Hello, everyone. Welcome to today's webcast, Beyond 100G, Upgrading Existing Networks, brought to us by ECI and Bar Data. I'm Michelle Coleman with NTCA. If you have questions, please use the Q&A box in the lower right-hand corner of the screen to submit them. Questions will be addressed immediately following the presentation. And at this point, I will turn it over to Dr. Scott Wilkinson, Senior Director of Portfolio Marketing at ECI Telecom.
Thank you, and welcome. Glad everybody was able to make it today. Just briefly, in case you haven't heard of us, ECI has been around for 50 years. We call ourselves the Elastic Network company. We build optical and packet solutions as well as cybersecurity solutions around the world, and do a lot of course, in the United States. Bar Data is a partner of ours. They're a value-added reseller of telecom equipment and network hardware. They support both next generation and legacy networks. And that's enough for the introduction. So let's move on to the actual stuff. As you heard, please make sure that if you have any questions, go ahead and type them in while you're thinking about them, and we'll come back at the end and answer any of them that were not covered. So briefly, what are we going to talk about today? The agenda is, why would you want to go to 100 gig? A lot of you, I'm sure, are looking at your networks and saying, 10 gig seems to be working pretty well, maybe 100 gig in one or two places, but why would I want to move beyond 100 gig? So we'll go through that a little bit. And then most of the time will be spent on what are the technologies there? What allows us to go beyond 100 gig? How close are they? How realistic are they? How easy are they to use? All of that about what are those technologies beyond 100 gig. And then I'm specifically going to focus on 200 gig because there's some really nice things happening around 200 gig today that make it a very economical interim step to going to things that are much further. And we'll give an example of what exactly I mean by that. And then we'll have conclusions and questions and answers at the end. So what's the problem here? Well, first of all, bandwidth demand is continuing to increase. That's good news for everybody. It means that we're going to stay in business for a long time. For a while, we thought that the bandwidth increase was going to be relatively slow. That has changed, and we obviously are going a lot faster than we had originally planned back about 10 years ago. That's great news. Video is the big driver everyone wants to talk about. The fact that Netflix and Amazon and all the others are delivering high-definition video all the time, on demand, to multiple devices, even over wireless and cell phones and all those other devices. This is a great thing for us. But there's more than just that happening. There's data center interconnect. There's moving applications from businesses and homes into the cloud. Businesses in particular are putting more and more of their things into the cloud, which just means a computer somewhere else, but you've got to have a high-speed connection to it. So there's a lot of other things going on within the network that are continuing to cause bandwidth demand to increase. Again, that's a great thing. It's a good problem to have to solve. The other thing that's happening is the capabilities of optical networks are advancing relatively quickly. For a while there, it took us a long time to get from 10 gig to 100 gig, and then ROADMs started showing up, and now things beyond 100 gig are coming really, really quickly, which means that the costs are coming down faster than we might have suspected, and they're getting easier to use a lot faster than we might have suspected. So that's putting some pressure on the network as well as in terms of how to determine what's the right thing to put in and when. One of the great things about 100 gig was that if you designed a network for 10 gig, it was pretty easy to migrate up to 100 gig. In fact, 100 gig sometimes even worked better than 10 gig because of the technology we were using. You could have networks that 10 gig wouldn't quite work on, and 100 gig would work even better. So that's a great thing. But then what happens when 100 gig is no longer enough? Can we continue to make that same statement that we can move a 10 gig network beyond 100 gig relatively simply? And that's what we're here to talk about today. So first of all, based on just empirical data, looking at what's actually happening out there, the transition to 100 gig and beyond, it's already started. One of the interesting things to look at on this graph, if you look at the blue, that's all ports that are shipped optical that are less than 10 gig. And the green is all ports that are shipped at 10 gig. If you look at this year, they're pretty much at parity for this year and next, which means everything below 10 gig added together is about the same as what we're shipping at 10 gig. So 10 gig is obviously doing very, very well, but look beyond this year into 2018 and 19, and 10 gig starts to drop off. Well, why is that? Because 100 gig is coming on stronger than anything we've ever seen. That orange line there is 100 gig. It's coming on very, very fast, and those ports are going to dominate within a year or two. That's impressive. And then when you start looking at the red line, 200 gig, it's coming up even faster than 100 gig did. 200 gig and beyond is growing very, very quickly. So this transition has already started in 2016, 2017, will be big in 2018, and then just continue to grow through the next few years. That's good news, especially for people like us who are building this equipment, but it can be confusing to people like you who might be trying to figure out what's the right technology to put in your network. So let's step back a little bit and talk about some of the fundamentals. At 10 gig, every speed up to 10 gig used a technology called on-off keying. What that meant was you turned a laser on and off very fast. As you went from OC3 to OC12 to OC48, you just turned it on and off faster, on-off keying. 1 bit per symbol, and it worked very, very well. It made sense, but the problem was when we got to 10 gig, we started to hit a wall, and there wasn't a really clear view of how we would go beyond that. There were some examples of things that were happening at 40 gig that never really did very well. Things like polarization mode dispersion, PMD, you may have heard of, and other optical and electrical limits really started making it increasingly hard to go beyond 10 gig to that next step. And so there was this huge sort of desert where 10 gig was commercially deployed, and we didn't see a really clear vision to where we were going beyond that. We were trying different things. Nothing was really hitting like it should. And then some very smart people looked at that and said, well, there's no reason to turn things on and off really fast. Let's look at what they're doing in the satellite world. In the satellite world, they don't just turn it on and off. They turn it on to different levels. So it's not just a 0 and a 1. It might be a 0, a 1, a 2, and a 3. And you can distinguish between those levels. So there's also this idea that there's a phase associated with light. It's a wave. So if you think back to your physics textbooks, there's a phase associated with that wavelength of light. And you can actually control that, which is what they do with satellite communications with wireless. So now that we have the ability to different levels and different phases, we can start putting more and more things out every time we send a symbol down. So you'll see these kind of constellations like this. You'll hear terms like QPSK and QAM. Doesn't really matter what those mean. All that it means is that where we used to be sending 1 bit, where it was either on or off, we now can send one of these dots. So for the simplest one, look at, say, QPSK on the far left. You have a level 0 and a level 1, and you have 2 different phases. Depending on which one you choose, you're sending one of those 4 dots. And at the other end, it figures out which dot it is and turns it back into 1s and 0s, and you've got 4 symbols, 4 bits. If you go up to the ones that are more and more farther up there, like 64 QAM, there are 64 symbols going out every time you turn that laser on and do something with it. But what you'll notice is those things are a lot closer together. So now your receiver has to be much more sensitive to be able to figure out, am I talking about the 3rd one up and the 2nd one over, or the 2nd one up and the 3rd one over? Because they're pretty close to each other, and I got to figure it out. But at least now that we have figured out how to do this, we've just got to make better receivers, and we continue doing this for a very long time. We have the potential to take this and go to much, much higher speeds. This is the fundamental technology which has allowed us to go to 100 gig and will allow us to move beyond that. There are some issues, though, and some 100 gig networks may not support those higher rates, which is what we're going to talk about. So if you look at where these things are going, I like this graph a lot because it shows you a lot of different things in a way that sort of makes sense, and it's also got some pretty colors. So along the bottom is the baud rate. So it's how fast are you sending out each of these symbols. And on the vertical axis is the modulation type, getting more and more complicated, more little dots on the graph. So if you add more and more dots, you're getting more information. And if you send them more rapidly with the baud rate, you also get more information. but they sort of have a trade-off in terms of distance. So if you look at the ones, the stars are the ones that ECI in particular has commercially available today. We can do, for example, look at that 100 gig dot. That's the QPSK that's been out for a while now. If you look at the line for 200 gig, which is the next line up, also in the green there, you'll see that there are two different technologies being used, either an 8 QAM or a 16 QAM. Why would you care about those two? Well, the 8 QAM, which you can see labeled as 8 QAM is on the modulation type, it's the lower one there, needs a higher baud rate, needs to send more symbols every second to get to 200 gig. But because it's a simpler technology, it's got fewer dots up there, it's a much easier receiver to figure that out and make it work. So it can go a longer distance. But you've got a faster baud rate, and there may be some trade-offs with that in terms of how much spectrum it takes, and we'll talk about that in a minute. So there are trade-offs. Alternatively, you can go with a lower baud rate, but you can't go quite as far. That's what your 16 QAM does. Moving on up, you're going to see things like 32 QAM and 64 QAM, and then you're going to start really having these trade-offs of how far can I take them. This is sort of what we think in terms of the state of technology today. If you look at the similar plot, I'm hoping in 5 years these will all look like ridiculously small numbers, and we've figured out how to go a lot further, but generally the trend will be the same. As you go to a higher modulation type, if you go to faster and faster baud rates, you're not going to go as far, but you can get more stuff on the wavelength. There have been announcements of things up to 1,028 QAM, so there's some really interesting stuff going on. But this is generally how it's working. New modulation techniques are allowing us to do more and more bandwidth on a wavelength, but often there's a trade-off in terms of distance and spectrum. What's really cool about these is because they're all basically using the same technology, picking different levels, picking different phases, sending a bigger constellation or a smaller constellation. All of that's programmable in most cases. So now you'll have the ability not just to pick one, but to say if that link fails and it's a long distance link and I need to go a different way and it's a shorter distance, I can change the speed on the fly. I can program it to go different. Or if I just want to buy one set of optics and go different distances with that set of optics, I can program them to be 100 gig or 200 gig or 400 gig or whatever they need to be to go over longer distances or shorter distances. You design the optics for the optimal performance. Today, you can buy optics that will automatically switch between 100 gig and 200 gig, either through programmability or through automated procedures. There are a lot more options coming, but this is really, really exciting about high-speed optics, that we're no longer going to be stuck with whatever you put in, and if your network changes, you have to switch it out. You now are going to be able to go in there and software say, I used to be going at this really high rate. The fiber has degraded over time. I can just knock the rate down a little bit and continue to run. That's very exciting. But one of the things that's going to be a trade-off is this idea of the grid. And if you're used to WDM, you've heard of the 50 gigahertz WDM grid. It's standard spacing defined by a standards body in the ITU, International Telecommunications Union. They have standardized on this 50 gigahertz WDM grid, which says if you're sending a wavelength, a specific color, it's got to fit into one of these little slots. And if it goes outside of that slot, it's going to get killed. And if it migrates a little bit one side or the other, it's going to get killed. And if you want to communicate to somebody else, it had better be in the same slot on both sides or they won't talk to each other. This has been the standard for years and years since WDM came out. We started with a 100 gigahertz grid, quickly went to 50 gigahertz, and we've sort of stayed there for a long time. It's been very useful because rates up to 100 gig coherent, the stuff that's deployed now, fit very well into this. 100 gig starts to get close to the edge. There are some 200 gig solutions that also fit in there pretty well, but some of them don't. We're starting to see the issues there. Now, our 200 gig fits within there, but some of them don't, and you really have to be very, very careful with that, because when you go over 100 gig and you start doing very high baud rates, the amount of spectrum required to send that can get more than 50 gigahertz. And now you've got a problem. And that's when we start talking about something called FlexGrid. FlexGrid, for those who haven't heard it, is the idea that no longer will we have a fixed 50 gigahertz grid? We'll have a grid where you can say, I need as many chunks of 12.5 gigahertz as you can give me. And if I need 50 gigahertz, I'll take 4 chunks. If I need 75 gigahertz, I'll take 6 chunks. If I need something bigger than that for a larger thing that's coming down the pike, I can take as many chunks as I need. This gives us room to grow. Higher bandwidth signals can now take as much as they need. We can stack the grid based on bandwidth requirements. It can be very, very efficient. You can move things in as close together as you want to. You're no longer stuck with a specific grid. It's a really great idea. And in fact, if you buy a ROADM, a reconfigurable optical add-drop mux, from most people today, it will be a flex grid-based ROADM, because almost all of them are now. The challenge is, when you go to flex grid, it's relatively difficult to manage, and of course, everything's got to be upgraded at once, because if you do this on one of them and the other one's not upgraded, you're going to start losing your signals, and that's a bad thing. In terms of why it's difficult to manage, well, think of something like this. If you've got a signal moving, say this 400 gig signal at A, and you need to go through a ROADM and switch it over to B, your network management may come back and say, yeah, I've got plenty of bandwidth over there. I've got plenty of spectrum available. The problem is it's not all together. It's not connected all together. I've got to do some rearranging somehow of all these signals so I have a gap big enough to stick that 400 gig in there. So something called active spectrum rearrangement is going to have to be required to make this kind of situation work. It gets even more complex when you look at something like a churn situation where you have a lot of wavelengths on there, and over time, some of them go higher in speed, some of them go lower in speed, sometimes they combine together. You can end up with these stranded bandwidth gaps throughout your spectrum that you now can't use at all. And you're going to have to do something, some sort of defragmenting to go through and combine these together and put them together. So imagine doing this kind of defragmenting across your entire network to make sure that the spectrum gets used well. It can be a very, very complicated problem, and something that we're working on. And the answer, of course, is the universal solution everyone wants to talk about, which is SDN, software-defined networking. With SDN, you have the concept of a system sitting above all of this, looking down on it, that understands I now have the need for a specific amount of bandwidth through the network. I can see where the spectrum is, I can see what the capabilities are, and I can tune the whole network to respond to that. That's where we want to get. And the ultimate future is what's really shown here, where there's something like a flexible client rate, where you go to a customer and don't just sell them 100 gig or 50 gig or 10 gig or something like that. You tell them you can change on the fly whatever speed you want in terms of your Ethernet connection or your packet connection. My optical system will then change the wavelength rate that's connected to it to match. My flex grid system will then adjust the flex grid to make sure it matches whatever optics, and then all of that is coordinated for the best possible performance based on measurements that are coming out of the network at any time. That's where we want to go. That's the ultimate end game. We're not going to tell you that today. No one's going to tell you that today, but we're going to give you the pieces that are going to allow you to get close so that this is where we can get to. So this fully automated, everything integrated together future is coming. It's very, very exciting stuff. I did want to take just 1 second to talk about the form factor of these optics themselves, because you may have heard terms like analog and digital coherent pluggables. I wanted to talk a little bit about what those are just so that you can understand where we're going. There's something called analog pluggables and digital pluggables for coherent transmitters, the kind of things that are doing those spectrums, those constellations we were talking about. Analog, what people do with analog is they take the digital signal processor, the digital part of this, and they pull it out of the pluggable optics and they put it on the circuit board. There's some real good reasons to do that. The digital signal processor is generally the most complex and power-hungry part of these optics. So by pulling them off the optics and putting them on the circuit board, you get rid of a lot of heat, you get rid of a lot of complexity, and you can make the optics generally smaller. So there's some great reasons to do that, and you see a lot of vendors who have done that as we've moved up in speed. Now, there's some reasons why you don't want to do that. One is you end up with generally a fixed format. So all this stuff about programmability of the optics going to different speeds, you lose a lot of that. Interoperability is a lot harder because the interface now between the optics and your circuit board is analog. And if anyone's ever worked with analog electronics, it is it's a lot harder to get those things to line up than it is to get digital electronics to line up. So there's an analog interface is generally more difficult to diagnose and harder to get to work together, but you end up with a less complex pluggable optics design, and you can get something out generally faster. So usually you'll see these come out first. But the ultimate, what we really want to get to, is digital coherent pluggables, where the DSP, that signal processor, that digital part, is integrated into the optics themselves, because now you have a digital interface between the optics and the circuit board. It's much, much easier to build that circuit board. It's much easier to put programmability, so you can do those modulation schemes and programmability around it. It's much easier to diagnose problems. The optics become more complex, though, so there is a trade-off there. You don't get all the functionality and the features, but you might get higher density. Generally, what people believe is digital is the long-term end goal for pluggable optics. Analog is sort of a step along the way, and what you might see is, for example, a supplier that sells their own analog that you have to buy from them that allows you to get some capabilities out of it, but you have to buy a specific one, whereas with digital ones, the hope is that eventually we'd get to some more interoperability there. So now we've built kind of the background for this. I want to talk a little bit about 200 gig. So it's very exciting to always read about 400 gig, 600 gig, and terabit, and the things that are going beyond that. But if you look at the requirements, you look at what you've got to do with your network, and you say, well, I really don't want to have to build out a whole new network with FlexGrid and everything that's associated with it. I really just need to find a way to expand the bandwidth that I've already got on my network. I've got 100 gig. I can put a few more wavelengths on. I've got a couple of links where maybe I'm going to have to expand that going forward. 200 gig is a great solution because it was specifically designed, at least in most cases, not everybody's, you have to be careful, to fit in that same 50 gigahertz grid and to run on the same networks that originally were designed for 10 gig, then were designed for 100 gig, and now can be designed for 200 gig. There's different versions to go different span budgets. Longer span budget doesn't necessarily mean longer. It could be going through a lot of hops, but they all fit within this 50 gigahertz grid. So 200 gig is a really great solution. In fact, you could even operate 200 gig as an alien wavelength on someone else's dim fiber network where they do the amplifiers and you do the wavelength. It allows you to delay that big network migration step that comes with moving to FlexGrid. You can put them on the existing network, move them into a nice place that you've already got them. This is a really good interim solution for people who are looking at expanding. And because it's such a nice solution, because it works so well, it's an interim solution that's going to be around for a while. People always look at things like this, like these steps in speed, and say, okay, well, if you look back at 10 to 40 on the long-haul network, I know 40 worked well inside the data center and some switches, but 10 to 40 to 100, a lot of people just said, skip the 40 and go straight to 100. It's going to come in, it's going to work just as well, I don't need the 40. In this case, the reality is if you skip the 200, you're going to have to do something else to go to the next speed because it's not going to fit in your network. You're going to have to make some changes. So for a long time, 200 gig is going to be a great solution that gives you that interim between I have to rebuild my network, but I need to get that new bandwidth out there. The brief commercial from us, just take this and say this could be from us or from anybody else, but if you want to know exactly what we do with it, we have a couple of different 200 gigs, and there's more and more coming all the time. You can do a simple 200 gig transponder where you have two 100 gigs in and a 200 gig out, super card. That's a really nice solution if you've already got a 100 gig network in place and you need to migrate some of those over to 200 to free up some wavelengths. Or you've got a bunch of switches that are now starting to run at 100 gig and you want to use your bandwidth more efficiently. It's a great solution for that. What's even cooler, though, is this thing on the right, which is an encrypted 200 gig muxponder, because with this one, it's got a little OTN switch in it. If you're not familiar with OTN, it's kind of next generation of SONET. We can multiplex a bunch of stuff together, but it's built to handle any kind of rate. So fiber channel and Ethernet and SONET SDH and InfiniBand and all those other things can be packed into this at 10 gig rates and below and hand off a 200 gig, and each one of them can be individually encrypted. This is the kind of power that's coming out now when we get to 200. And what we call this is per service encryption. It's very simple, works very well. If you're not familiar with optical encryption, go to our website, read up on it. It's a really, really great idea. Encrypts everything in the payload, no delay added to the network. It's become very, very popular. But per service encryption is the idea that you may be able to, you may be talking to a lot of end customers, be they your own internal or enterprise customers outside, say a hospital that needs encryption versus a school that might not, and each of them individually can be encrypted with their own encryption key. It's a great idea. It allows you to have a faster return on investment for your 200 gig. For example, if you were to offer it as a premium service, we've shown that there's an improved ROI of about a month to 2 months because the cost of 100 gig versus 200 gig is not that great difference, and the cost of encryption versus not having encryption is not that huge of a difference. So in every case we've studied, there is an improved ROI going to something like a per-service encryption model, going to 200 gig. And I highly encourage you to check if you're looking about going to 100 gig, look at the 200 gig, and then look at something like this. There's some really nice features starting to come out when you get there. I did want to give an example. So if you have a network, and this is just an example network, has some ROADMs in it, has some point-to-point links. It's deployed. It's got 100 gig on most of the links. There's a few links between major sites where the capacity has been reached, where 100 gig is now starting to look like it's just not going to be there forever for you. What do you do? Well, there's some options, of course. You can add fiber, and if you happen to be fiber rich, I was at a trade show recently with a potential customer who was talking about their network, and we were talking about going to 200 gig, and his answer was, I own my own infrastructure. I have 40-something fibers in every duct. I can just use another fiber. It's kind of hard to argue with that unless you don't have 40-something fibers in every duct that you own and doesn't cost you anything, which is just about everybody. So fiber is always an option. You can add routes. You can call up your local dark fiber supplier and say, hey, I need to go a different direction. I need to add a new route. I need to do something here. That's always an option as well. It's relatively expensive, but it allows you to build up more routes. You could decide, this is the point in my life where I need to upgrade to FlexGrid. Going forward, I know I'm going to go to 400 gig. I'm going to hit a terabit at some point. I know this is going to happen. I have the cash in hand. This is my time to do it. And that's, for some people, the right answer. And it depends on your situation and what your link looks like. Or you could do something like, it says Apollo, that's our brand name, but it could be a 200 gig that fits into the existing network and allows you to double the bandwidth on any or all of these links without making any other changes. That's absolutely the lowest cost option. It gets you to double your bandwidth. And if you're looking at your network and saying, doubling my bandwidth is going to last me for years, this is obviously the right solution for that. It allows you to delay or eliminate the need for an upgrade of your entire network. So for example, if you had just this link from A to B, very simple, it's a point-to-point. You're looking at that point-to-point link and saying, that one is really starting to run out of space. I need to do something to upgrade it. That one you might be able to justify going in and putting FlexGrid on both ends. It's just taking one link down, rolling it over to another one, upgrade the whole thing, put in 200 gig, put in 400 gig, wait if you want to, but it allows you to make that conscious decision that maybe in this limited space, I can go ahead and move to FlexGrid and move forward. But if you have services that go somewhere else, if you have something more complex, if it hits more than one span, if it goes through a couple of ROADMs, that's a more complex upgrade. You're going to have to plan that out. You're going to have to make sure that every service around it is not affected, and you're going to have to replace everything in there to go to FlexGrid. I don't want to discourage you from doing that. We will sell you the equipment to do it. It's a great thing to do. You're going to probably want to do it eventually anyway. But if you don't happen to have a lot of cash around, and you're looking at those spans and saying, upgrading to 200 gig is going to last me for years, why not go ahead and do that? Put in 200 gig, run it over the same wavelengths that you were running 10 and 100 over without having to change any of the other hardware. It's a really, really nice solution. And that's what 200 gig gives us, by the ability that it's able to work within that spectrum by doing some really fancy things with the multi-layer and multi-phase stuff. 200 gig was designed specifically to make this work. So I know I talked a little bit fast. I do want to spend a little bit of time on the conclusions. spend this time asking questions if you have any, because I know you've blocked off the whole hour and you've got 30 minutes to ask questions. Why not use them? The point I want to make here is that there are a lot of bandwidth drivers pushing the limits of existing networks. Most of us are seeing these. Either it's coming from your end users who are asking for greater and greater speed to the home. There was an ad at the beginning of this webinar. If you logged in early enough, about talking about gig, being gig to the home and getting a certification for that. So as you drive a gig further and further out into the network, 100 gigs doesn't start to look quite so big anymore when you're talking about gigs going to individual businesses and homes. So there are a lot of drivers pushing the limits of existing networks. And the reality is 100 gig is the new 10 gig, because 10 gig is the new 1 gig. It used to be that backbones were based on 10 gig, not anymore. Backbones are based on 100 gig. It used to be that 10 gig was the new pluggable, not anymore. 100 gig is the new pluggable. And 1 gig is now what we're talking about giving people at their homes. That's just amazing. When you think about the old modems that you used to have that dialed up, and when they got really, really fancy, they got to 56 kilobits. It's just hard to imagine that we've moved to 1 gig, and now we have all this streaming stuff going on. It's a great world we live in. The technology to go greater than 100 gig is there. Once the breakthrough was made on coherent receivers and these multi-layer, multi-phase transmitters, we had a way now to move beyond 100 gig. Every couple of months, you're seeing a new announcement. Most of those are out of labs, but occasionally you'll see new product announcements. Next year, you're going to start seeing more 400 gig announcements. You're going to start seeing 600 gig announcements. There have been lab announcements up to a terabit. It's just going to keep coming. Not all of them, obviously, are going to apply to everybody. Most of them, you're going to look at just happening maybe on the really big web scale guys or the undersea. But as those guys break new ground, it allows us to eventually make those more commercially available, more cost-effective, and bring them back into the network. And it's something you have to start looking at and be planning for. But as you're planning for it, always remember 200 gig is a great upgrade solution. If you've been looking at your network and saying it's starting to creak a little bit around the edges, starting to burst a little bit at the seams, I can't think of any other analogies, but you know what I'm talking about here. It's starting to get a little bit packed. 200 gig is a great way to upgrade without having to make that leap to the next generation. And with that, in a brief 35 minutes, I've covered everything that I wanted to cover here. I do want to thank everyone who dialed in and those who are downloading this and listening to it later. Here's some contact information with VARdata, our regional sales manager, Dina. My name is on there as well if you'd like to contact me. And at this point, we'll go over and see if there are any questions.
Thank you so much, Dr. Wilkinson. At this point, we will open it up for your questions. You can type them in the lower right-hand corner of your screen, and we'll take those questions as they come in. First question, Scott, is it okay if we post this presentation on our website?
Yes, please do. So for those of you who want a copy of this, it will be posted on the website. Okay,
great. And we'll post it next week. If you go to for those who missed it or you want to share with your colleagues, just go to ntca.org and go to the Events tab. There you will see webcasts, and you can look under the archive webcast, and it'll be there. Great. We'll do have a few questions. There have been announcements about higher speed optics for short reach inside data centers. How does that technology line up with what's described here?
Yeah, good question, because the technology inside the data center is very different. They can do things like put multiple lasers together to go over one link, because they don't use WDM inside the data center generally. So you'll see announcements about things like 100 gig and 400 gig, very short reach distances by putting a lot of signals in parallel, or you'll see terms like PAM4 and a bunch of other technologies that are coming out. The goal inside the data center is to get a lot of bandwidth over a short distance with a very small transceiver. So what they're doing is great, and it actually helps a lot, because when you get more bandwidth inside a data center and off of the switch, that means more bandwidth outside the data center, which uses this technology. So they're working very much in parallel, but it can be confusing sometimes. Just be careful. When you see a data center optics announcement at 400 gig, they're generally talking about going a very short distance. It's not necessarily applicable to going outside, and it generally doesn't work with WDM, so that's the only signal on the fiber.
Okay, next question. If I need to upgrade to 100G in the near future, should I go ahead and make the leap to 200G, wait for 400G, or just go with 100G for now?
It's another good question. What I would highly recommend is if you are looking at making that leap, if you say your 10 gig network is running out of steam and you are seriously looking at 100 gig, talk to somebody about 200 gig, because I think you'll be surprised that the cost differential is not that great between them. And if you believe that you're going to need it at some point in the future, it would be nice to be able to go ahead and get that in now. And you saw from the hardware that I showed, there's some very versatile ways of doing that. Devices that will bring a lot of signals together and take them up to 200 gig. So making the move to 100 or 200 makes a lot of sense. Now, should you wait to go to 400 or higher? It depends on whether or not you want to be on the cutting edge. Most people who are building relatively smaller networks don't want to be on the cutting edge. Unless you are a Google or a Facebook or an eBay or one of those kind of guys that has a really big, very expensive network, you probably want to wait a little while on things like 400 and 600 gig, because they're just going to start rolling out next year. Let the kinks get worked out, let the prices start to come down before you start looking at that.
Okay, are the rates beyond 100G expected to be interoperable? Can I buy from anyone and have them work together?
Yeah, I get this question a lot, or a variation on it, which is, can I buy gray optics or from somebody off eBay or off of a reseller site and plug them into anybody's networking equipment and make it work? The reality is, once you get to 100 gig, those optics right now at least are very complicated, and there may be limited cases where you can plug them in on both ends and get them to work, but you'll probably have to default to the lowest common denominator, so that's not going to go the long distance. You probably won't get any performance monitoring out of them, which is very important to have when you get to those speeds. So most vendors are going to tell you, you really need to buy those optics from us, and you need to have both ends be the same optics to really guarantee it. There are exceptions. There are examples that you will see out there. There's things like the Open Rotem project where they're working to try to make these as interoperable as possible. But if you talk to people involved with those projects, what they'll say is, yes, we can make them work together, but the only way to do that is to cut out all the features and make them work at the very, very basic level. So I think that answers the question that, yeah, it might be possible, but the reality is in most cases you're not with 100 gig, and certainly with anything beyond 100 gig, for performance monitoring, for better performance, and to make sure that it actually doesn't heat up and get too hot inside the equipment and all the other things that come along with that, you're going to want optics that were certified by the supplier. These things are much more complicated than stuff below that.
And what's the maximum rate per wavelength?
Theoretically, there is a maximum. There's something called the Shannon limit, which says there's a certain amount of bandwidth you can put into a certain amount of spectrum on a fiber. We're not that close to it. People are doing some really exciting things. The only place it's really starting to show up as being an issue, and it shouldn't be an issue for anybody on this call unless you happen to have an underwater network, and I don't think anybody here is worried too much about that. The undersea guys are starting to see us encroach a little bit on what's called the Shannon limit, which is the limit of how much bandwidth you can put onto a fiber. And then the question is, what do you do beyond that? One analyst is starting to call that the optical glass ceiling. What do we do when we reach the edge, and what's the industry going to do? I don't know. There's been some interesting sort of speculation about multi-core fibers or finding ways to do really weird things with the physics inside the fiber. But the answer is there is fundamentally a limit. We're not close to it, at least terrestrially. Undersea, they're going to start worrying about it. They will solve it first, and then we can take advantage of that.
Okay, looks like those are all the questions we have. Thank you so much, Dr. Scott Wilkinson, Senior Director of Portfolio Marketing at ECI Telecom. I'm Michelle Coleman with NTCA. Thank you so much for joining us, and have a great day.